Okay, hi everybody. So let's take a look at these next 5 exercises. So let A and B be 2 unit vectors that are perpendicular to each other. Let f of t, this is a curve now, be equal to this expression. And cosine, sine, you should think circle. Typically, we have A is sort of the vector 1, 0, and B is the vector 0, 1. And so this is then equal to cos t, sine t, which literally is the circle you're used to. But we can use any unit vectors whose dot product is 0. And that's what we're going to prove. Show that this curve lies on a sphere of radius 1. So actually these vectors can be in any dimension as long as they're on the sphere. So maybe A is like over here. Its endpoint is on the sphere, and B has to be at 90 degrees to it. And then we can use them to make a circle that goes around the sphere. And we can even do this in higher dimensions as long as A and B are unit vectors whose dot product is 0. Okay, so this is how to make circles in higher dimensions. Let's check that it lies on the sphere of radius 1. So if the length of f of t is equal to 1 for all t, then it's on the sphere. Okay, so now the length squared is equal to 1 squared, which is 1. And that's better because this is the dot product times the dot product. Now let's use the formula for f of t, which is this. So let's take cos t a plus sine t b. That's a vector, dot product, cos t a plus sine t times b. That's a vector. Let's take their dot product. We get cosine squared t a squared plus, and now let's do, let's do this one first. Sine squared t b squared. Plus now the cross term, so we get a cos t sine t a dot b and a cos t sine t a dot b. So that's actually 2 cos t sine t a dot b. But if we choose a dot b in any dimension that are perpendicular to each other, this whole thing is 0. And then a squared and b squared, if their unit vectors are both equal to 1, so this becomes a 1, this becomes a 1, and we're left with cos t times plus sines. We're left with cos squared plus sine squared, which equals 1. So yeah, it's on the sphere. Done with number 3. Let P and Q be 2 points on the sphere in any dimension. Let this, L of t, be the line connecting P to Q. So remember chapter 1. You should know this right away from chapter 1. If there exists a value of t between 0 and 1, this means that 0 is less than or equal to t less than or equal to 1. So if there's some value of t between 0 and 1, where L of t is the origin, is the 0 vector, then show that t has to be a half and p has to be minus q. So like if we're in 2 dimensions, this means that, if p is here, then if q is here, the straight line does not pass through the origin. But if q is equal to minus p, then the straight line from p to q actually does pass through the origin, and the value of t, where it'll pass, is 1/2. So this is pretty intuitive, but we're going to prove it on any dimension at once. So let's see. If there exists a value of t such that L of t equals 0, so let's use the formula for L of t. L of t equals p plus t times q minus p. And if that equals 0, where 0 now is like 0 vector. So in any dimension, it would be like 0, 0, 0, whatever. But we can just write a big 0 for the 0 vector. Okay, well then we're supposed to show that t has to be a half and that p is equal to minus q. So let's manipulate this formula right here. Okay, so p plus tq minus tp. So that's 1 minus t times p plus t times q equals the 0 vector. Let's see. I'm not seeing it right now. Let's see. If there exists a value such as t is 0. Wow, I'm somehow drawing a blank. Let's see. Well, let's come back to that one. I am just not seeing it right now. Why does it have to be? I just don't know how to do it in formulas. Like from the picture, it's obvious that this must be true, but let's see. What did we not use? Okay, so P and Q be 2 points on the sphere of radius 1, centered at the origin. So we didn't use that yet. So what if we do this? Like, okay, in other words, in order to get the fact that these are unit vectors, we are going to have to take norms. But let's actually put them on opposite sides. So let's put 1 minus t p equals minus tq. Now we'll take the norm, because that will allow us to use the other assumption that we had, that p and q are points on a unit sphere. Okay, so when you take norms, remember that like it pulls out with the absolute value times the norm of the vector, if little c is a number. So then taking norms, we get the absolute value of 1 minus t, which remember, t is between 0 and 1, so 1 minus t is also between 0 and 1. So actually we can just we don't even need the absolute value, times the length of p, which is 1, equals now the absolute value of minus t, again, t is positive, so the absolute value would just be t, times the length of q, and that is 1. And so now we see that 1 minus t is equal to t, which means 1 equals 2t, and 1/2 equals t. Done. And now we just need to show that p is equal to minus q. So back here, if we plug in, now that we know that t equals 1/2, we get 1/2 p equals minus 1/2 q. Multiply both sides by 2, and we get p equals minus q. Okay, there we go. So whenever you get stuck, look back at the problem and see if there's any like piece of information you didn't use. So once I saw I didn't use p and q are norm 1, I knew that I had to take norms. Okay, let's do number 5. Let p and q be points on the sphere. Okay, assume that this is not true. Okay, show that there exists a curve joining p and q on the sphere of radius 1. Okay, so we know in the previous two problems, we know that for any 2 points p and q that are not on opposite sides, then this line, this straight line, will not go through the origin. Okay, and we know a formula for this straight line. That line was L of t equals p plus t times q minus p. Okay, and now what we do is, all these points here, they're inside the sphere. They don't have length 1. If this was the Earth, they're cutting through the core of the Earth. So what we want to do is move every point out to the sphere. And we can do that by normalizing, by making it unit vectors all along the curve. So our new curve, I'll call it C of t, it'll be L of t divided by the length of L of t. So this will be a number, it'll have square root of sum of squares of horrible things. Another way we could write this is we could just use the formula for L of t. It'd be p plus t times q minus p divided, so this is a vector up here. And then we're just going to scale the vector by a number. We're going to divide it by this number, which will depend on t. And so it'll scale at every point, no matter what the value, it'll scale it out by the right amount so that it's on the sphere. That's it. Hint, divide L of t by its norm. That's what we did. Okay. Okay, let's do number 6. Now, if p and q are unit vectors such that p equals minus q, so they're on opposite sides, show that there still exists a curve joining p and q on the sphere of radius 1. Right, so in the previous exercise, we produced this curve that goes from p to q along the sphere, provided that they weren't on opposite sides of the sphere in any dimension. Now we're going to show that even if they are on opposite sides, there still exists a curve joining p and q that stays on the sphere. It's just that we can't use this formula anymore because we'd be dividing by 0 if they're on opposite sides. Okay, so you may assume that there exists a unit vector A which is perpendicular to p. Then use exercise 3. Okay, so here's p, here's our cartoon, here's p, and here's q on the opposite side. It's equal to minus p. So we can't just put the line through and then divide by the norm, because right there, the norm will be 0. We can't divide by 0. So we can't use our previous formula. But instead, we're allowed to assume that there's a unit vector A that has 90 degrees with respect to p. And then all we do is we just say, okay, well, c of t is equal to cos t a plus sine t. Actually, maybe we should do cos t p plus sine t a. And then if t equals 0, we get c of 0 equal to cos of 0 is 1, and sine of 0 is 0. So we just get p. That's great. Now if t equals pi, cos of pi is negative 1, so we get minus p. Sine of pi is 0, so the amount. So basically we just go whoop, and we turn around, and we go from p to minus p, which is also called q. Okay, let's do number 7. Parameterize the ellipse by a differentiable curve. Okay, so what does an ellipse look like? Let's choose obviously, like, there can be ellipses that are centered at other places, but these are harder. Essentially what we'd use is we'd use this vector and this vector, and then we're going to do cos t a plus sine t b. So now here, a and b do not need to be unit vectors, not necessarily unit vectors. If they are unit vectors, then we're going to get a circle. But we do want them to be perpendicular. Okay? So anyway, let's take the ellipse. What was it? X squared over a squared plus y squared over b squared equals 1. So this is actually a much simpler ellipse. It's not as complicated as this one, because I believe the point a comma 0 is on this ellipse. Let's check. If I plug in a, I get a squared over a squared is 1, and I plug in 0, I get 0. So this would be 1 equals 1, and this is a point on the ellipse. Similarly, 0 comma b, if I plug in b for y, 0 for x, the equation is satisfied. And so actually what this ellipse looks like is this really nice ellipse here. Okay, let's call a comma 0 capital A. Let's call 0 comma b capital B. And then what we're going to check is that this curve lies on the ellipse. So let's check. Does it satisfy the equation of the ellipse? Well, if we see what a is, it's a comma 0. If we see what b is, it's 0 comma little b. And then c of t, if I expand it out, what's the first coordinate? Top number will get cos t times little a plus 0 times sine t. A cos t. And then the bottom number, I think you can check, is b sine t. So we can write that as a column, or we can write it with the commas. It doesn't matter. Now let's check that it satisfies this equation. We have to plug in this number for x, plug in that number for y, and what we get is what? A squared cos squared t over a squared when I plug in for the x. B squared sine squared t over b squared when I plug in for y. And the question is this equal to 1? Cancel, 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 cancel. Cos squared plus sine squared is 1. Yes. And so this formula also gives us ellipses if we choose a and b appropriately. Okay, so now we're done with number 7. Let f be a differentiable function in two variables, and all we know about it, we don't know its formula, but we know that its gradient at the point x is just some scalar multiple of x. Okay, and this holds for all the x's. Then show that f is constant on any circle centered at the origin. And here's the hint. Put x equals a cos t, y equals a sine t, and find df dt. Okay, so let's just do what they told us to do. So, okay, so let's draw a picture first. Can I even remember the question? So what was the question? It asks us about some function of two variables. Maybe I can write f of capital X. And we don't know the formula, but we do know that the gradient at any point capital X is equal to some number times capital X. That's what we know. What we want to show is that this function is constant on any sphere. So let's pick a sphere of radius a. A sphere is a circle in 2 dimensions. And what we're going to do is, if it's constant, so then if you take any points, p and q, then we need to show that f of p is equal to f of q. Okay. Now, what we do is we join p to q by a differentiable curve. Okay. And so I guess what this is saying is let x equals a cosine t, and let y equals a sine t, because we're on a circle of radius a, so that's like sort of a that up and a right. And so that's c of t. C of t equals a cos t. Oh, I messed up. A sine t. And now f of c of t, well, if c of t is going to be on this circle, and so if f has the same value at every point, then f at every single point of this curve should be constant. Should be constant. Is it? Well, this is now a single variable calculus function. So single variable calc says if the derivative is 0 and on a connected interval, which this is going to be connected, t will go from 0 to 2 pi, which is a connected line segment in the real numbers. And so if the derivative is 0 on a connected line segment, interval of numbers, then we know from single variable calculus the function is constant. Okay? And that would prove what we want, that this function takes the same value at every point on the curve, which can get us, basically all around this circle. This curve parameterizes every point on the circle, including these ones that I drew. So let's just take the derivative. So the derivative of this, d dt, by the multivariable chain rule is the gradient of f at c of t dot product c prime of t. Now, what do we know about the gradient? It's equal to a sum constant little c times the point. So this is equal to sum constant little c times the point itself, which is big C of t. And then we have to take the dot product with c prime of t. And we're hoping that this is 0. So is it 0? Well, let's take a look. What's c of t? C of t dot c prime of t. So first let's calculate c prime of t. Derivative of cosine is minus sine. Derivative of sine is cosine. So when I do the dot product, c of t dot c prime of t, I will get a times minus a cosine minus a squared cos t sine t. And then I have to add plus this times this, which is a squared cos t sine t. And that is 0. And so any constant multiple of it times it is also 0. And so we're done. Okay, so that's number 8. Exercise 8 is a special case of exercise 9. Let f be a differentiable function in any dimension, and assume that there's some function h so that the gradient is equal to just basically some number times that actual point. Okay, so it's oriented outward from the origin. Maybe I didn't draw that last time, but like if here we are in space, and let's say this is your point capital X. So capital X is also a vector, and this function has a gradient of f at capital X. That's a vector, and of course in general that could be this vector, right? But that is not, and if I drew it this way, this vector is not a scalar multiple of this one. What we're saying is that if the gradient is always some multiple of x, it could be longer, could be shorter, could be this way, like at every point it could be facing towards the origin. That would be this situation. Or at every point it could be facing out the origin, like that. But if the gradient of f at x is just some function of x times the actual vector x, so here's a number times a vector, then sort of our picture looks like it's sort of all radiating outward or inward in different ways. And that's a very special case. It actually happens in physics a lot. If that's true, then f is constant on every sphere. Okay? And so they just basically tell you how to do this. I mean, we've done it already. So just take a moment to read this part that I'm highlighting. So basically, no matter what dimension, we proved in the previous exercises that any points on the sphere can be joined by some curve, C of t. And then what we'll do is we'll take f of C of t, and that's a function of single variable calculus. So if its derivative is 0, then it is a constant function. Okay, so we just take the derivative by the multivariable chain rule. This is the gradient f of C of t, dot product C prime of t. And this gradient here is equal to, by our assumption, some function of c of t, this is now just some number that we don't really know nor care about, times the vector c of t, dot product c prime of t. But we've shown before that if you're on a sphere, then this is always 0. Right? If you're on a sphere, this is always 0. Why? Well, because on a sphere, c of t dot c of t is 1. And so apply d dt to both sides, we get the derivative of 1 with respect to t is 0. And the derivative here is 2 c of t dot c prime of t. And so 2 is not 0, so this must be 0. And that finishes exercise 9.